All right, so can you tell me the question?
Yes, so it's saying find a number b such that the function f equals the function g. And it's giving that both f and g have a domain of 3, 5. And f, or function f, is defined by the formula f of x equals x squared minus 3. And function g is defined by the formula g of x equals 18 over x plus b times x minus 3.
Like that?
For g, it's b parentheses x minus 3.
So 18 over x plus b, and then like this, right?
Yes.
Okay, so we want to know when are these two functions equal to each other. So you just set them equal to each other. So if f is equal to g, well, that means we have x squared minus 3 is equal to 18 over x plus some b times x minus 3, right? So now, well, we actually need more information. Let me see if I can pull up the question from my book. So what is f of 3? So let's find those values. Now we want this to hold, right? But first let's figure out what are these functions on the domain. So if you find f of 3, you plug in 3 into the function, you get 3 squared minus 3, and that gives us 9 minus 3, which is 6. Now, what is f at the last endpoint of the domain? You evaluate that, you get 5 squared minus 3, which is equal to 25, right? Minus 3, and that will be 22. So these are the function values at the endpoint of the domain. Now let's evaluate g at the same domain. So for g of 3, we have 18 over 3 plus b times 3 minus 3. So that's just 18 over 3. And, well, b times 0, that will disappear. So that's g of 3. And what is g of 5? G of 5, it's going to be 18 over 3 plus b times, so x is 5 minus 3. That would give us 18 over, oh, sorry, I think I miswrote this one. Should be 5 in here, 18 over x. So that would be 18 over 5 plus b times 5 minus 3, that would be 2. So this is really 18 over 5 minus plus 2b. Now we want to know when are these functions equal to each other, right? So f of 5 happens to be 22, and g of 5 happens to be this piece, right? We want these functions to be equal. That's what we want it, right? Right here. So for the first endpoint, we don't have to do anything because there's no b, right? B disappears. So there is really nothing to find b value of so that they're equal to each other. Regardless of what b is, it's fine at that endpoint. So we just need to work on the second endpoint. When are these functions equal to each other? So we're setting up f of 5 is equal to g of 5. And you set these two equal to each other. F of 5, we found that to be 22. And g of 5, we found that to be 18 over 5 plus 2b. And this will allow you to find the value of b, so that way these function values are equal to each other on this specific domain. Does that make sense?
Yes, but why did you choose to use 5 instead of 3?
Oh, because here B doesn't survive, it's 0. So you can't really solve for B because B doesn't even come into the picture. Because we're solving for B such that these two functions are equal to each other.
Okay, I see.
You see that? So when you plug in 3 into G, regardless of what B is, 3 minus 3 is 0. So there's no way we can solve for them, solve for B if we set them equal to each other. So the only way we can do it is by taking the second portion, f of 5, setting it equal to g of 5, and then just simply solve for B algebraically.
Okay.
Uh-huh.
Okay, because I had thought that you would set g of 3. No, I mean, I thought you would have set g of 3 and f of 3 and g of 3 equal to each other, but I see like why that wouldn't work.
Right. So if you do f of 3 equals to g of 3, there's nothing to solve because f of 3 is 6, right? And then g of 3 is just 18 over 3. They're just two numbers. It doesn't make sense to set them equal. There's nothing to solve because b doesn't survive, right? 3 minus 3 gives us 0. So this kind of eliminates b from the picture.
Okay, I see.
Okay. All right. Does anyone else have any other questions?
I was wondering if you could go over odd and even functions.
Sure. So for odd functions, we have to remember this rule. So if you have f of negative x, that will give you negative f of x. That means the function is odd. And if you have f of negative x equals to f of x, then that means f is even. Now, how do we use this when we try to show if two functions, if a function is odd or even? Let's take an example. So say I give you a function. Let f of x be equal to, let's come up with something. Let's do x over x minus 3. And we want to know if f is odd or even. Okay, so the way we're going to determine that is by simply plugging in a negative x and see what it simplifies to. Does it simplify to negative times the original function, or does it simplify to simply the original function itself? Okay, so let's plug in negative x into this function. So if I evaluate f at negative x, what do I have? So I plug in negative x here and negative x here and just simplify that. So we have negative x over negative x minus 3. And if you simplify this, I pull a negative out from top over x, and I pull a negative 1 from the bottom. So that gives me x plus 3. And then the double negative, I can cancel them. So I get x over x plus 3. Well, now, what does that mean? Does it look like the original function? Or does it look like negative times the original? Or is it none of it?
Is it negative times the original?
Well, you see, this is the original function, right? So if I want it to be negative times the original, it will be negative x over x minus 3. That will be the negative times the original. But is that what we have here?
Oh, so it's neither?
It's neither, right? So pretty much you apply the definition and then you try to see, does it look like the original function or does it look like nothing? If it doesn't happen to be any of those, then we can claim that this function is actually neither. So f is neither. F composed with its inverse of x gives you x. And the second one was the reverse of this. So that would be f inverse composed with f gives you x. If these two composition holds, then we know these two functions, f and this function that we're calling inverse, are indeed inverses of each other. Now, often, if you want to show two functions are inverses of each other, you kind of do decomposition in both directions. Now, do you have a specific question you want to show this property on?
I wasn't looking at any specific examples. I just remembered that I had a little bit of trouble on it while I was reviewing it. I'm not sure if you could find an example. It was in 1.5.
1.5. Okay, so let's see if we have an example. Pretty much we just take two functions and do the composition in two directions. So let's see if we can find a question from the homework. So I'm just going through the book and see if I can find one. But if you guys do find one, you can give them to me while I'm looking. Okay, so for this problem, so let f be equal to, let's say, 4x plus 5 over 2x plus 3, and say g is equal to 3x minus 5 over 4 minus 2x. And we want to show, or let's say determine, because we don't know if they are, right? Inverses or not. So determine if f and g are inverses of each other using the inverse function property. So all of that instruction. So I'll have you guys just think about it for 1 minute, and I'm okay. So you want to show that you want to compose f and g, and you get x, and then we'll also do g with f, and we'll show that gives us x as well. So let's do that. So we have f of g of x. Now, this problem is actually going to be long because these functions are both rationals. So f, if I plug in g into f, well, that's going to be what? 4 times x plus 5 over 2 times x plus 3. Now, what is x? Well, x is going to be g. So that will be 3x minus 5 over 4 minus 2x, and 3x minus 5 over 4 minus 2x. So that's the setup for f composed with g. So let's go ahead and simplify that. Okay, so for the top, we get 4 times 3x minus 5 over 4 minus 2x plus 5. So I just kind of separated the fraction line, all over 2 times 3x minus 5 over 4 minus 2x plus 3. Okay, and just continue to simplify until everything becomes just x. So let's see if that happens. So now here, you kind of want to put them in the same fraction using the common denominator. So you can write this as over 1 and multiply it with 4 minus 2x over 4 minus 2x. And we'll do the same thing with this one, put them in the same fraction. So write 3 over 1 and multiply it with 4 minus 2x over 4 minus 2x. Okay. So continuing on, so if I do that, I'm able to combine the top into a single fraction. So we have 4 times 3x minus 5 plus 5 times 4 minus 2x over 4 minus 2x, same denominator, all over we do the same thing on the bottom. We have 2 times 3x minus 5 plus 3 times 4 minus 2x over 4 minus 2x. And then we kind of distribute a combined like term for each of these. Here we distribute the 4, here we distribute the 5, and do the same thing on the bottom. Clear things up, distribute 2, and distribute 3 here. So what do we have on top? We have 12x minus 20, and for the second one, we have 20 minus negative 10, right? Yeah, 10x. All over the denominator, 4 minus 2x. All over. Now on the bottom, we get 6x minus 10 plus 12 minus 6x. All over 4 minus 2x. And here a lot of things will cancel. So let's see. So the 20s, they cancel out. So that gives us what? So 12x and negative 10x, that's just 2x. All over the denominator, 4 minus 2x. Over, now on the bottom, 6x and negative 6x, they cancel out. So you have negative 10 and 12, that will be just 2 over 4 minus 2x. Now you guys know how to simplify this? Do you guys remember keep, change, flip?
Yeah, I remember that.
Right? Yeah, so that's what you're gonna do here. So this will give you 2x over 4 minus 2x, and the division, we change it to multiplication and reciprocate. So that's 4 minus 2x over 2. And finally, these will cancel out. So we're left with 2x over 2, and that is that happy x. Cool, right? Whew, that was a long problem. But we wouldn't have like this long, but the idea is the same, right? Doesn't matter what function, you're showing that the composition, when you do the composition this way, you get x as a result. And now you also have to show this one. Both of them has to be x. If both direction you get x, then they're inverses of each other. So I'll leave that up to you to show, but pretty much you plug in f into g now and simplify just like we did it right here. Brianna, does that make sense?
Yes, so if you do g of f and that also equals x, and that means that they're inverses of each other,
Exactly.
right?
Mm-hmm.
But would there be like also a shorter way to do it? Because like originally I had thought that, well, no, I guess it wouldn't work like if you set them equal to each other and solve for x, correct?
Right,
To
you
see
wouldn't do
if-
that. No.
Yeah.
You wouldn't do that because that wouldn't make sense. So
Mhm.
another way to do it would be to actually find the inverse formula for one of these. So
Oh, yes, yeah,
yeah.
that also. So I would find like
Exactly.
the inverse of one of them and see if
Yeah.
that would match
The other one.
Yeah, okay.
Yeah. So that will be another way to do it. Unless the question says use the inverse function property, then you have to do it this way. But if it just says, are these function inverses of each other, then you have two options, either inverse function properties or compute the inverse formula for one of them and show it is equal to the other one.
Okay, thank you.
Cool, yeah. But this is the inverse function property where you do the composition in two different directions and you get the identity function for both compositions. Okay, all right. Any other questions? Okay, are you guys okay with finding inverse formulas?
Yeah, I think so.
Yeah, so why don't we like continue this problem and see if if we take one of these, f or g, and see if we get the other function, right? So why don't we take, so which one do you guys want to take and find the inverse formula of, f or g?
Can we do F?
Okay, so let's take f and find its inverse, and we'll show that that is actually equal to the function g right here. So let's do that. Let's see what that comes out to be. So I'm just going to copy this and put it right underneath. Okay. So if I give you any function, you should be able to find the inverse formula by doing the following procedure. So we want to find the inverse function of x. So the first step is to let f of x be equal to y. And then rewrite the function. So then we have now y is equal to 4x plus 5 over 2x plus 3. And the next step is to switch them, switch x and y. So we have now x is equal to 4y plus 5 over 2y plus 3. Okay, once we switch, now we just solve for the variable y. So the way we're going to solve it is multiplying both sides by 2y plus 3. So that gives us x times 2y plus 3 is equal to 4y plus 5. And then we want to isolate y, and y happens to be in two different places, here and here. So how do you go from here? What do you guys think? Any thoughts?
Don't you distribute the x?
Good. So we distribute the x here, and that gives us x, well, 2xy plus 3x is equal to 4y plus 5. Now I see that I have a term involving y here and here. So I want to put them together so I can use the GCF method to factor. So you can decide which side you want to pull y to. I'm going to put y on the left side and everything else to the right side. So let's go ahead and subtract 4y from both sides. So you have 2xy minus 4y, and I'm also going to subtract 3x from both sides. Okay, so I'm doing two things at the same time. Is equal to now, so on the right hand side we have 5 minus 3x. Let me know if you guys were able to follow that. So I did two things at the same time. Was that okay?
Yeah.
Okay, cool. So now continuing on, now on the left-hand side, you see both of them have y in common. So I pull it out because initially we wanted to solve for y. So that would be y times 2x minus 4 equals to 5 minus 3x. Now finally, we divide both sides by 2x minus 4, and that will isolate y. So indeed, y is equal to 5 minus 3x over 2x minus 4. And now, lastly, you want to recall this is the inverse function. So just rewrite. So our inverse function of x is equal to 5 minus 3x over 2x minus 4. And there you go. That's the inverse formula.
I have a question.
Sure, Eva.
So, like you pulled out the y, like
Mm-hmm.
a couple steps up. Is there a reason why you also don't pull out 2?
Oh, because we're only solving for y. We don't need the 2 in there.
Okay.
Yeah, because initially our goal was to find the inverse formula. So we let y be that formula, switch x and y, and then you're solving for y. So even though 2 is a GCF, but we don't want to pull it out. We just want to pull out the y.
Okay, thank you.
Mm-hmm. Yeah, no problem. Okay. Yeah, so that's the inverse formula. Now let's check, right, if that looks like G. Does it? Hopefully it does. 3x minus 5 over 4 minus 2x. Yeah, it's the same thing. It's just the negative in a different place. So if you rewrite this function, pull out the negative sign, you'll see it looks exactly the same as the one we're given. Cool. So this is good. Now, do you guys remember how to relate domain and range with f and its inverse?
Wouldn't the domain of the inverse be the range of the original function, and the same for the vice versa?
Yeah. So this is the range of f, and the domain of f is equals to the range of the inverse. So make sure to know that property. It's very useful when it comes to finding domain and range and all of that cool stuff.
Can we actually go over a problem, maybe one that's a little bit like simpler and not like too long to do, to find the domain and range of a function and its inverse?
Okay, yeah, so let's do that. So say I give you a nice simple function. So let f be equal to, let's see, let's do a square root of x minus 2. Okay, so let's do, let's see if this is nice. Well, it'd probably be not so nice, but let's use that function, right? Why not? It's a function. And we want to find the domain and range of f. Now this is actually, you know, I'm going to change the function because you can just graph it and find the domain, so you don't have to worry about the inverse. Let me give you something where you do have to worry about the inverse. So say 1 over x minus 2. Let's do that one. So we want to know the domain and range of f. So who can tell me what's the domain of f? Now for the domain, we can just look at the function and observe, right? What makes sense and what doesn't make sense. So what do you guys think? What will be your approach to this type of problem?
Is it all real numbers except when x equals 2?
Right, everything except when x is not equal to 2. So the domain would be negative infinity to 2, open, union, 2 to infinity. So the reason this is the domain is because the entire real line makes sense, but 2, because when you plug in 2 here, we get 1 over 0. 1 over 0 doesn't make sense for us. It's undefined. So we got the domain. But for range, well, we can just look at it. Well, maybe for this one, we can look at it and determine, but we don't want to do that. We want to actually use the inverse function to figure out the range. So we know that the range of a function is equal to the domain of its inverse function. So if I can find the inverse formula and then compute its domain, that is my inverse formula. Sorry, that is my domain of this. Does that make sense, guys?
Yes.
Okay, so let's do that. So let's find f inverse. Let's do that on the side. So I'm going to let f of x be equal to y. So that means we have y is equal to 1 over x minus 2. And then we switch them. So we get now x is equal to 1 over y minus 2. And then I multiply both sides by y minus 2 and try to isolate y. So we have x times y minus 2 is equal to 1. Here we distribute x on both sides. We have xy minus 2x is equal to 1. And I'm solving for y, so I add 2x to both sides. Xy is equal to 1 plus 2x. And finally, I divide both sides by x. So we have y is equal to 1 minus 1 plus, 2x over x. And thus our inverse function is 1 plus 2x over x. Cool. So that's a nice inverse function. So what's the domain of this function?
All real numbers.
Almost. Correct, you're almost right. But you see how we have an x on the bottom? That means there might be an x value when it is actually 0 on the denominator.
So x can be all real numbers except for 0.
Exactly. So everything except 0. So the domain of this function is going to be negative infinity to 0, union 0 to infinity. And that is the range. So that answers our question. So you do need to go through this one extra step of finding the inverse formula. Once you have it, find its domain. That is your range if the question asks for range of a function. Let me know if you have any questions. Okay, well, any other questions you guys want me to go over?
So professor, so the domain that we found for the inverse, the domain that we found for the inverse would be the range of,
F.
oh no, I'm sorry.
Mhm.
The domain of the original function would be the range of the inverse function as well.
Exactly. So
Okay.
this would be, so if the question asks you to find domain and range of the inverse function, well then, you know, domain of F is the range of the inverse. Yeah, so good point. So pretty much the takeaway is your domain of the original function is the range of the inverse, and the range of F is the domain of the inverse. That's how we relate F with its inverse formula. Okay, and also remember how to evaluate inverse function because we did that too. So any other questions? So let's complete the square for a quadratic. So so let f of x be equal to let's see. Let's do 2x squared minus 6x plus 1. And we want to, you know, find everything, meaning we want to write f in standard form, then identify the vertex, and then determine if it's a max or min, and then find the max value and all of that. Okay, so everything that we can possibly find for a quadratic, we'll do that for this one. Now, what's the a value for this quadratic? Who can tell us?
The a value would be 2.
Good. So a is this coefficient right here. That's 2. So if a is positive, right? So if you recall from our class notes, if a is positive, what's the shape of the quadratic? Is it facing up or facing down?
It's facing down and looks like a U.
Looks like a U, so it's facing up. Yeah, so it's gonna look you like this. So that's actually what I mean by facing up, right? Well, I don't know if that's like facing up, but your parabola opens upward, right? So it's like a nice happy face.
Oh, professor, just like a little side question. So this, when you want to find the standard form of a quadratic function, it's like saying you want to find the vertex form.
Right. So standard form is another way of saying vertex form. So I didn't use that terminology because the book doesn't use it, but if you know it by that, that's fine. Which is really f is equal to a times x minus h squared plus k, where you have the vertex, so it makes sense to call it vertex form rather standard form, but it means the same thing. Good point. Okay, So if A is positive, we have a nice parabola looking this way. So that means our vertex is this point. So is that a max or min?
Minimum.
So this would be a min. All right, so we already know all of that. Now let's go ahead and find the standard form of this. So now because the coefficient is not 1, so you want to force it to be 1. So you pull out that constant from both of these terms. So I'm going to pull out a 2 from the quadratic term and the linear term. So let's rewrite. We have f of x. We are going to leave a space. And then from 2x squared and negative 6x, I pull out a 2. So that gives me x squared minus 3x. And I'm going to leave a space and just rewrite plus 1. So now let's go ahead and complete the square for this portion. So the formula says to take b over 2 and square it. Well, our b happens to be negative 3. So that would be negative 3. You take half of it. That's, keep it as a fraction. If you have a calculator, you could convert to a decimal, but I would keep things in fraction form. It's fine. So 3 over 2, and then we square it. That will give us 9 over 4. So that's what goes in here. 9 over 4. Now, what do we place on the other side to keep a balance?
Would it be 9 over 4 plus 1?
No. So ignore the plus 1, right? Think of it, it's not there. We're just working with inside the parentheses, okay?
Oh,
So
9 over 4 times 2.
exactly, because the extra term we added is this guy right here, 2 times 9 over 4. So we also need to add a 2 times 9 over 4 on the left-hand side. So it keeps a balance. And now bring in that 1 because that's given from the initial problem. Right, so the 1 is just there until the very end, you combine it with the extra constant. Any questions so far? Okay, so continuing on. So now that we figure out what goes on both sides, now let's write it as a perfect square. So on the right-hand side, we have 2 times our perfect square, which is x minus b over 2. That's 3 over 2. And we still have plus 1 waiting outside. And on the left-hand side, we just simplify that. We have f of x plus 9 over 2, because 2 over 4 simplifies. And finally, to solve for f of x, we subtract 9 over 2 from both sides. And that gives us f in standard form. F is equal to 2 times x minus 3 over 2 squared. And so 1 minus 9 over 2, put them in common denominator, they'll be negative 7 over 2. So there you have the standard form of this quadratic. Any questions?
Wait, why did you put x minus 3 over 2 in the parentheses?
So
What's that?
this right here, this factors into x plus or minus that determines from the b. So it's b over 2 all squared. So remember, when you have x plus bx, and when you add this extra term, b over 2 squared, this factors into x plus b over 2 squared.
Okay, I see.
Now our b is negative, so that's where we got the minus from. So it's minus b over 2. Good. Any questions? Okay, now let's go ahead and identify the vertex. So what's the vertex for this parabola? So the vertex will have x coordinate 3 over 2 and the y coordinate negative 7 over 2. Right? This is the x coordinate and this is the y coordinate. Now, as we mentioned, it's a minimum. So if I do a rough sketch, let me just see the y-intercept 1. So we know the y-intercept is 1. So it's probably here. 3/2 and -7/2. Let's estimate. That's really small, right? Maybe somewhere here. Okay. Yeah, not looking good. Hopefully you guys can see that this is a parabola going up. So here's the vertex. That's 3/2, and this is the y-coordinate, -7/2, and this is the y-intercept. Now there are x-intercepts here. You can find them by setting f of x to 0, but they're probably not nice points. I didn't really work it out. But if you want, you can find them. But pretty much that will be a rough sketch of this. So the minimum value, it's going to be -7/2. And then when does it occur? So this occurs at x equals 3/2. And now can we talk about the domain of this function? What's the domain and range of this function? What do you guys think? So this is a polynomial, right? Of degree 2. What's the domain of this function? Can we plug in anything? So look at the standard form. What do you guys think? Does everything make sense for this problem? Come again, Brianna?
Oh no, that wasn't me.
Oh, that was you. Oh, Ragda, go ahead.
Yeah, I said for the domain everything fits in.
Everything, right? Yeah, so that's right. So for the domain, everything, because you can plug in any real number here and it makes sense. Nothing makes it undefined. So therefore, the domain is -∞ to infinity. Now, what about the range of this function? Now, if you want, you can find the inverse function and do all of that we did before, but you don't really have to for this problem because you can look at the graph and observe what's the lowest y value and the highest. So what do you guys think will be the range of this function?
I would say from -7 halves and then infinity.
Exactly. So the range is the lowest to the highest. So the lowest it goes is -7/2 and all the way to infinity because it's keep going up. So by looking at a graph, we can also find range and domain. Okay, so that's pretty much it, everything about a quadratic. Standard form, vertex, determine if it's a max or min, what's the value, when does it occur, and domain and range. Now you could also talk about increasing and decreasing stuff that we did. Let's write it out, right? Why not? Since we already have an example. So can you determine where is f increasing? So increasing is when it's rising, right? We talked about that very briefly also. So it looks like the function is increasing where? So right here, it's going up. So it's increasing from 3/2 to infinity. And then where is it decreasing? It's decreasing from here. So that's from -∞ to the x-coordinate of the vertex. So there you have two more detail of this function. Okay, so any other questions or any questions on this? Okay. All right, well, let me know if you guys have any other questions. I'll stick around a couple more minutes, but if you don't have any more questions, you're good to go. continue studying, and also remember to take a break. Don't overstudy, okay? Study enough so that way you're prepared. Don't stress too much. Review the homework questions and just go through our quizzes, the solutions, so that way all of that makes sense as well. Okay, so say you're given 2 points, 3, -1, and 5, 10, and we want to find the equation of the line passing through these 2 points. Okay, so pretty much for a line, you need 2 things. You need a point, which we have 2 of them actually, and you need the slope. So let's go ahead and find the slope. So for the slope, we use the formula. Slope, we write it as m. M is equal to y2 minus y1 over x2 minus x1. And then we select our points and label them. So let's call the first one x1, y1, second one x2, y2, and just plug them in. So we have 10 minus -1 over 5 minus 3. That will give us 11 over 2, and that is your slope. So we found the slope, and we have points, right? Now using any of the 2 points and the slope, you can write out the equation of the line by using the point slope form. So the point slope form is y minus y1 equals m times x minus x1. You can use that, but if you're not comfortable with this one, you can use the slope intercept form, where you do have to go and find the y-intercept. So it will be an extra work, but hey, whichever way you feel comfortable, doesn't matter. So let's go ahead and plug in our x1, y1, and m. So when you use this format, you have to plug in these guys. So which point do you want to select? Let's select the first one. Why not, right? So we select that one, plug them in. So we have y minus y1, that's -1, equals m, 11 over 2, x minus 3. And now simplify the double negative. So this is just y plus 1 equals 11 over 2, x minus 3. So that's the equation of the line. Now, of course, you can move things around and write it in many different ways. If I want to go from here to slope intercept form, I would have to just simply solve for y. So let's go ahead and do that. Why not, right? So let's write in y equal mx plus b form. So we have, I will have to distribute the 11/2. So you have y plus 1 is equal to 11/2 x minus 33 over 2. And then we add 1, subtract 1 to both sides to solve for y. Y is equal to 11 over 2x. And then 33 over 2 minus 1, that will be 35, negative 35 over 2. So that's the same line, but expressed in a different way. Now, if you want to get rid of those fractions, you can just continue working on and multiply both sides by 2. You have 2y is equal to 11x minus 35. That's another way to write the same thing. So you have the point slope form, slope intercept form, and then that's just another way of writing. We can call it the general form of a line, okay, where you don't have any fractions. Okay. Does that make sense, Brianna?
Yes, it makes sense. And if they only give you 1 point and they want you to find an equation, how would they format that question?
So
like, what would the
so if I give you 1 point, I will have to give you either the slope, or I will also have to give you one of the intercept, or I will tell you find an equation of a line through this point, but maybe parallel to this line, so that you can get the slope from that line. are perpendicular to that line so you can get the slope. So either way, you have to be given another condition so that way you can determine the slope somehow.
Oh, okay.
Mhm. All right,